Okay. So today I'm going to be doing another presentation regarding machine learning. This time the topic is on logistic regression, and we're just going to go through the basic idea of logistic regression. So let me go ahead and start. Okay. So what is logistic regression? It is a classification algorithm, which I know is kind of strange, given that the name is logistic regression. I didn't do the naming, somebody else did. I'm not sure what the reasoning behind that was, but just know that it's used for classifying a group of data points. So what that means is that the probability, it gives a probability that an example belongs to class 0 or class 1, or the positive class or negative class. You know, the naming, as long as the naming is consistent, you can call it 0, 1, even 2, 3. It's just up to like you to keep it consistent. And so we have some examples, such as classifying emails as spam. So it's either spam or it's not. Or classifying a tumor as malignant or benign. So it's either malignant or not. So for the logistic regression, what your goal is to do is to create a hypothesis function, which gives you this probability of whatever you're trying to predict. And so the hypothesis function, you can see my mouse, right?
Yes.
Okay, good. I want to make sure that you guys can follow along. So here is the hypothesis function, and I'll explain real quickly what these different variables mean. So as said before, h is the hypothesis function. In this case, as opposed to h being equal to like a linear function, like I mentioned in my previous little seminar about linear regression, h is correlated to a nonlinear function, and the way that happens is by giving h to like this function called g, and g is a sigmoid function essentially, as you see below here, and so h of x equals g of theta times x, and theta times x is just really your parameters of however many for like, and your your theta times x are your parameters and attributes, and like how that is described as like a little function, and then that line, that function itself is passed through as z through this g of x. So, and what you get when that happens is a number between 0 and 1, and that acts as a probability. So to clear things up, h of x is the probability that y equals 1 given the input x. So if your h of x equals 0.7, that means there's a 70% chance that the output is 1, or inversely, there's a 30% chance that the output is 0. And to better visualize that, say your z, when z is greater than or equal to 0, so when z is on this side of the graph, that means g of z is greater than or equal to 0.5. And thus, since h of x is equal to g of z, h of x itself is greater than or equal to 0.5. And from your classifier, you can predict that y is equal to 1. And then when z is less than 0, so on this side of the graph, g of x is less than or equal to 0.5. And therefore, h of x is less than or equal to 0.5. And you can predict that the class of this example is equal to 0. So say, for example, you have a data set that looks like this. you clearly have one class over to the side of this line and another class underneath it. Here, the line is z, and z is of the form theta 0 plus theta 1x plus theta 2x2. And given that h of x is equal to g of z, you would plug this into like the sigmoid function and find the probability of when h of x is greater than 0.5. And then you can like make your prediction if it's, let me explain a little better than that. So what you can do is set your z to greater than or equal to 0, because as discussed on the previous slide, when that happens, h of x is 0.5, and thus you can predict that y equals 1. So with this line, z equals -3 plus x1 plus x2. And I had like 1x, just to show that 1 is theta 1 in this example, and also theta 2. So you can solve for this equation, and as you see, when x1 plus x2 is greater than or equal to 3, h of x is greater than or equal to 0.5, and you can say that the class is equal to 1. So for example, here's 3 for x1 and 3 for x2, and you can see that the its value would be over here, separated by in this class. Whereas if it's 1 plus 1, it's that's less than 3, so therefore it's the other negative class. And furthermore, you can do this, you can separate data using nonlinear equations. So right here, you have your examples. One class falls within a circle, and a circle can be described as x1 squared plus x2 squared equal to like the radius. In this case, the radius is 1. And so your z value, or your z, would be equal to -1 plus x1 squared plus x2 squared. And when that is greater than or equal to 0, the y equals 1 condition is met. So you can classify these values as being equal to 1, and then these values being equal to 0 when x1 squared plus x2 squared is less than or equal to 1. Now, when you first start off with the data set, you're not going to start with a perfect, you're not going to start with the perfect h of x. You're going to have to like change that value in order for it to become the correct classifier that will give you the correct predictions every time or most of the time. And in order to do that, you need to calculate how far off your values are, how far off h of x is from the actual value y. And for that, we use a cost function. And your goal is to minimize the cost function, because when the cost is 0, that means there is no error, and that means that your hypothesis function is correct and like it works well with the data that you've been given. Also, you guys can stop me anytime if you have any questions. I'll try and answer to the best of my ability. So here the cost.
The AI portion, Ajalon?
What did you say?
Is that the AI portion of things where you're trying to minimize the constant function?
Yeah. That's where like the whole like machine learning kind of like actually starts happening, because it's like taking the your current hypothesis function and trying to change it to where that it fits the data. And so here is your cost function, and it's a little different from the linear regression. It looks like a piecewise at first, but we can eventually combine it into one little equation. But so here, when y equals 1, you have this equation for your cost function, and when y equals 0, you have this other equation. And because of the way that like for example, you can combine these those two equations into one, because when, let's say, y equals 1, over here you have your the for when the case for when y equals 0, uh, and it'll just disappear because 1 minus 1 is 0, and so like that whole portion, that whole term is gone, because we multiply anything by 0, it's 0. And same thing here, if y equals 0, this first term is going to be taken out of the equation, and then you're only going to be left with the cost function for the case that y equals to 0. And we can go a little bit more into like the separate cost function equations. So down below and on this side, you have the case when y equals 1. That was negative log of h of x. And what this means is that when the actual value of your example is 1, and then your h of x, your hypothesis, what it predicts, depending on what it predicts, that's what the output of the cost function is. So for example, if your hypothesis function predicts that the example is 1, like the actual value, like the probability is 1, then there's 0 cost because it lines up with what the actual value is. On the other hand, if you go over here and like your h of x predicts a value equal to 0, very close to 0, you're going to get an extremely large cost, because that's completely wrong. And then same thing for when y equals 0, so the actual value is 0. And when h of x predicts that the example probability is 0, then there's 0 cost because that's what it's supposed to be. And then it approaches infinity the closer that h of x is equal to 1, because that's a greater error. And so gradient descent is how we minimize the cost function. And if you remember from calculus, minimizing or the derivative of a function, like when it's set to 0, that means that you've gone to the minimum of that function. And so therefore the weights, when that's 0, the weights don't change, and you can say that you've converged to the appropriate weights parameters for your hypothesis function. And then alpha, quick note, is the learning rate. So that's essentially means how much your weights are going to change between each update, whether you can make it like 0.001 if you want to be really slow, and just there are advantages and disadvantages to having like a super small alpha learning rate, or even a super large learning rate. But like usually less than 1 is pretty good route to go. And then here's what the actual cost function looks like when you take the derivative. It kind of looks similar to the linear regression, but remember that h of x in this case is equal to that sigmoid function 1 over 1 plus e to the negative z. So it is like the actual output would be different than what the linear regression would produce. And so that's your gradient descent. And then as an overview for logistic regression, you're going to set initial parameters, alpha less than 1, and then beta, your parameters can be a 0 and 0. Perform gradient descent by calculating the partial derivative of the cost function and setting the parameters to the new values, and repeating until convergence. And then you can now use your hypothesis function to predict the new value. So for example, with the malignant versus benign, if you have a different data point, you want to see where the probability that it's malignant or benign, you can now like run it through your hypothesis function, and based on like the previous data, it can predict that whether or not your tumor is cancerous or not. And that's logistic regression. So if you guys have any questions, I'm free to clear anything up.
Quick question.
Yes.
So, what language are you using to run these models?
So I'm taking the Coursera machine learning class, and they use MATLAB, but you can also they use MATLAB because it's pretty easy to implement these things just because of like the way that they use matrices as opposed to like having a bunch of for loops, which I don't know, kind of complicates things. And like you can another reason I think it's because yeah, there's just a lot of built-in functions within MATLAB. But you can definitely do these things with Python or C++ or any language. I'm pretty sure Python has like libraries for you to do matrix type calculations. So yeah.
Ajalon,
Yes.
before we wrap up, since this is going to be seen by other people who may be onboarded into our team and other people who may want to find out about the Coursera class, can you tell us a little bit about yourself, your program, and your year and what you're doing?
Sure thing. So I guess I'll start with the beginning. My name's Ajalon Kilpatrick. I am currently a junior in the College of Engineering studying electrical engineering. Within the UM Innovate team, I'm currently working on the airway fire and like also helping out with prostate cancer research from time to time. And I guess I'm not sure what else I should say.
No, that's fine. And thank you for putting this together. And we're looking forward to working with you more on the healthcare projects, especially today after meeting with the nursing school. So this particular presentation and these algorithms will probably be used in the AI AR prostate cancer research project with UHealth. So thank you, Ajalon.
Of
Thank
course.
you.
Yes, thank you all for coming.
Appreciate it.